So for the home audience, I'm just going to recap. The first semester we talked about rates of change and slope, which we call the derivative. And this semester our focus is going to be on area and accumulation, which we're going to end up calling the definite integral. And we're going to talk more about the name definite integral and the notation probably tomorrow and on Monday. But for right now, we're going to think about area and accumulation. And sometimes it's going to have a very real world meaning. Other times it may not. Let's take a look at when it's going to have a very real world meaning. Let's see. Gabby, read for us, please.
As you drive on the highway, you accelerate to 100 feet per second to pass a truck. After you pass, you slow down more to a more moderate 60 feet per second. The graph shows your velocity, you see, as a function of seconds t since you started slowing. Okay, so does that look like you can see that you're going fast and then you slow down? Does that graph seem to agree with what it's saying, the story? Mm-hmm. All right. Liz, read for us the first question, A.
What does your velocity seem to be between t equals 30 and t equals 50 seconds?
All right, so this is, I think, the easier of the questions. Now, yeah, Gabby said it. Go ahead, say it. 60. Can someone give me what the wrong answer was going to be for the velocity between 30 and 60? If you're totally mixed up and confused, you might say?
0.
Yeah, why would you say 0, Liz?
Because it's that would be like acceleration.
Yeah, so you might think that you're looking at position, you're like thinking about the slope, right? So we're not talking about slope right now, we're just talking about, this is the velocity graph. We're looking at the graph of velocity. All right, so Gabby says, look, from like 30 to 50, is it 20 or 30? 30 to 50, it looks like we're going around 60, what are the units? Feet per second. Okay. All right, Liz, what's the second part of that question?
How far do you travel in time to go 30?
All right, does someone want to take a shot at that? How far did we actually go from 30 to 50 seconds? Betsy, you want to? 20 what?
20 feet.
Tell me why.
There's 30 seconds. 20 seconds.
All right. I agree with you that you've gone 20 seconds.
We did 60 feet per second, sorry.
Okay. 60 times 20. So 60 feet per second, and you've traveled 20 seconds, and that gives you 1,200. What are the units? Feet per second times second? Feet. Does that make sense? Isn't this rate times time equals distance? Is that right? Can I show you something? Say yes. Yeah. Thanks. Didn't we just find the area of that rectangle? Yeah. Didn't we do that? 20 seconds by 60 feet per second. The area of that's 1,200 feet. Can you see how I already said we were going to talk about area and accumulation and how that's sort of what we're doing? Mm-hmm. And let's think about the first problem we probably looked at first semester. I probably gave you position, and we looked at velocity. What's the slope of position? What are we looking at now? We're looking at area of velocity and getting. What do we get when we look at the area under that velocity? Yeah, we're sort of getting distance, aren't we? Isn't that strange? Oh, come on. Come on!
Strange.
It is. That's a little like coincidental, don't you think?
I just don't understand what the rectangle has to do with it.
How wide is this rectangle?
20 seconds.
How tall is this rectangle?
I understand that it's 1,200 feet, but I don't understand why the area of the rectangle has anything to do with finding the distance.
So what's distance equal to?
Applying.
Yeah, distance is equal to the rate times the time.
But the rectangle doesn't mean anything.
I'm actually saying it does.
Okay.
I'm actually saying it means a lot. I'm actually saying that the area under a rectangle, if it's velocity, actually tells you how far you went.
Okay.
All right, so we'll do a few more, see how it sinks in, and if it's still feeling funny, we can talk about that. Yeah.
Let's say the y-axis were ranged between negative 20 feet and 100 feet.
I don't want to talk about that yet.
Okay.
It's not a bad question. You're asking what does negative velocity mean? Oh, all right. So, all right, great. This is good. All right. I think we just did part B. Okay. C, read for us, Zach.
The distance traveled between equals 0 and 2 equals 20 can also be represented as the area of a region bounded by the curve. Count the number of squares in the region, estimate the area of the square to the nearest square.
All right. So the argument here is that if we could look at this area to tell us how far we went from 30 to 50, which was easy, you could also do the same from 0 to 20. Now, what's not so nice about 0 to 20? It's not a square or a rectangle. So they're asking you to please count up the number of squares and do your best to approximate to the nearest tenth. So they're not going to come out perfectly, but you're going to have some that are going to be whole and some that you're going to have to be like, oh, that looks like 0.5, that's 0.7. So go ahead and do that. I'll give you like 20 seconds, and then we can sort of try to come up with a class consensus. What do you say? 28, 27. Would anyone say it's less than 27? Anyone say it's more than 29? All right, so around, I'll say 28. That's fine. We're approximating. And a lot of what we're doing for the next few days, if not weeks, are going to be approximating. And some of you aren't going to like it. Some of you are going to be like, oh, come on, but that's only about, and that's okay. We're counting squares, so we have around 28 squares. So what's the wrong answer for how far did we go?
28 squares.
Yeah, all right. Actually, that might be a little more right. 28 feet would definitely be wrong. We have to look at what each square is. All right, so Gabby, each of these little squares is how wide?
5.
And each of these squares is how tall? 10 feet per second. Good. So I'm actually claiming that the area of that square is telling us a distance. And as a matter of fact, if you take 10 feet per second times 5 seconds, get 50 feet. So what's that, 1,400? So around 1,400 feet. Is that all right?
Wait, where do you get the 50 from?
5 times 10.
Each little block,
Yeah.
right?
Okay.
Is that all right? Do you want to ask a question? We're counting squares. How fun is that?
Writing graph paper, please.
No, but let's actually let's diverge a little bit. I don't know if we finished that question. If we didn't, we can come back to it. You can actually do this on your calculator. I'm going to take a look at x squared plus 1. Whoops. No, I'm not. Now, if we look at the function x squared plus 1, now this is, I'm going to move away from sort of like velocity. I'm just going to look at the area under the curve. Okay, so sometimes it's going to have a meaning because there's a context. Other times it won't. I'm going to go to my window and I'm going to go from 0 to 3, and my y-axis I'll go from 0 up to 10, and I think that should do it.
What was the thing about right there is very
What is?
It shows you what it looks like once you change the numbers. See how this
The
graph
bottom
right
screen.
there?
This thing?
Yeah.
Oh,
Once you
that's nice. So, if I asked you for the area under this curve,
it might be hard to do, but your calculator, if you actually go to second format, which is second zoom, you can go and you can turn the grid on. And if you turn the grid on and you go back to the graph, you can start to visualize the squares. All right, so maybe this is your workaround for graph paper, but if I went and grabbed it now, can you see can you see the squares?
Yeah.
Why aren't they squares?
Because of the way it's configured.
How's it configured?
Well, it's made so that
The scale, all right, the scale is messed up a little bit, okay? But do you see how you could maybe get a somewhat of an approximation by counting and approximating? Now, I'm not sure if this is going to work, so hold on. Would you agree that each square in here has an area of 1? Is that all right? Yeah, you would. All right. I think, let me see if it works. I'm going to go to my window, and I'm going to do, window, and I'm going to put my X scale at 0.5 and my, come on, all right, hold on. I promise I'll, 0, X scale 0.5, and Y scale 0.5. And now if I go back to my graph, all right, so can you see actually how you could probably be more accurate counting your squares? But what's the downside?
Can't you make an actual grid?
I don't think so.
Because
If
there's
you find out, let me know.
There's so many little spots you have to punch in, cover up, and stuff.
So what's the downside?
Too many
There are
squares.
more. There are a lot more of them.
We don't want to count all
So the more squares you have, the better you can be. But the downside is you got to count them.
Yeah.
Now, in this scenario, each one of these blocks is not 1, right?
Yeah, because of the scale.
Right. Gabby says each one has an area of 0.25. Half times a half. Okay? So you'd have to take all the blocks that you counted and then multiply it by 0.25. So can you see counting squares is a strategy you could use to find the area? It's approximate. The more squares you use, the better, but the more squares you use, the more annoying. Is that all right?
The X and Y square 2?
So you want to use fewer squares. So yeah, you could totally do that. And your answer is going to be a lot less accurate, but it's going to be a lot easier to do. And actually, okay, what would be ideal? How many squares should we use?
1.
No. Other way. An infinite number of squares. And each area of the infinite number of squares, what would the area of that square be? Tiny, close to 0. All right, so first semester, we did slopes. And the slopes were all 0 over 0. Guess what we're doing now? Now we're doing areas of infinity times 0. We have an infinite number of teeny tiny squares. Isn't that what Newton would tell you to do? Just take an infinite number of them.
Yes.
Yes? Anyone else with a yes? Take an infinite number of them and try to add them up.
Yeah, in order to see where they're going in the long run.
Yeah. Okay. So not for today, but we're getting there. All right. I've never seen you all so it's the end of the day. That's what it is. You'll be better at next week. You'll be in practice, the routine. Mm-hmm. Adrian's not going to be better ever. Okay. Sorry, there's nothing really to do but laugh at you, collectively. You're just such a pathetic lot today. All right. So we looked at a graph. Actually, you could also, if you wanted to, you could look at a table. And if you thought about looking at a table. Whoops. Oh, great. Never mind. Let's just let's go down to 4. All right. Betsy Reed, please.
Our car comes to stop 6 seconds after the driver applies the brakes. While the brakes are on, the following velocities are recorded.
All right, so we have this table of velocities that are recorded, and the velocities are getting smaller and smaller because we're stepping on the brakes. Does that make sense? Okay. All right, what's the fastest that we could have been traveling during those first 2 seconds, just looking at the table? What's the absolute fastest we could be going for those entire 2 seconds? Kaylee? Yeah. Unrealistic, right? Probably wouldn't be going 88 feet and then all of a sudden at 2 seconds stop to 45. But do you agree the fastest, the upper limit would be 88 feet per second? Does that work? Mm-hmm. All right, so if we were traveling at 88 feet per second and we know that we were traveling for 2 seconds, Tali, what's the farthest we could have gone if we were going 88 feet per second for 2 seconds? 176.
What?
Yeah, you're doing the right thing. You're multiplying by 2, right? Yeah. So the farthest you could have gone is 176. We actually call that the upper limit. Let's look at the lower limit. Hey, Adrian, what's the slowest we could have gone for the first 2 seconds? Yeah. Again, unrealistic that you'd be going 88 and then all of a sudden drop down to 45. But it certainly represents the absolute lowest limit. So, Derek, what would that give us for the shortest distance we could have gone? 90 feet. So there's an upper limit, there's a lower limit. Hey, you know what a good guess might be? Of course! Right? Add them up, divide by 2. Isn't that sort of like when we were taking the slope to the left, the slope to the right, and then averaging them? Oh, come on, say yes.
Yes.
Thanks.
It's like reversing almost.
All right, so 176 feet, 90 feet. All right, finish it up. I'd like let's see, maybe we should do it together. All right, so for the first 2 seconds, the furthest we could have gone was 176, or 88 times 2. What's the furthest we could have gone for the seconds 2 to 4?
90 seconds. Oh, sorry.
You can say it, but use the right units.
Oh, okay.
Wait, what are you asking?
From 2 to 4, what's the furthest we could have gone from 2 to 4 seconds? 90 feet. And for the last 2 seconds, from 4 to 6, 32. So the best overestimate you could say was 176 plus 90 plus 32. I can't do that in my head. 298 feet. The best underestimate, all right, well, let's see. 90 plus 32 plus 0. Yeah. What do you get? 122. All right, now, I need to give you some terminology, okay? We actually did approximations here, okay? We did approximations with delta t equal to 2. Does that make sense? We used delta t equal to 2. We took approximations every 2 seconds. In this specific problem, delta t equals 2 gives us the number of intervals that we're looking at is 3. So sometimes you're going to see the book refer to n, where they'll call them intervals. Let's think about what we did. We used 2 seconds. We did from 0 to 2 was our first interval. From 2 to 4 was our second interval. And from 4 to 6 was our third interval. So do you see how delta t is 2 and we have n equal to 3? N is the number of times that you took approximations. We took 3 approximations and added them up. Is that all right? Because in the book tonight, they're going to say, oh, what is it if n equals 4? What's your best approximation going to be? Never mind, that's a bad question, I'll just say. As n gets bigger, the more approximations you do, delta t is going to get smaller, and the better your approximation. Now the problem with this table, we couldn't do anything better than what we did. But can you see, this is sort of like Gabby's strategy, right? What if we just said delta t was 6? Her over approximation would be 6 times 88, which I don't know, is like 500 something. It's definitely an overestimate, right? But guess what? 298 is a better overestimate because it's smaller. So the more intervals you use, the better it is. Is that okay?
Mm-hmm.
N is the number of intervals, like from 0 to 2, 2 to 4, 4 to 6. Or it's the number of times you took approximations and added them together. If I go back to x squared plus 1, if I go to, let's see, my table, I could have approximated by saying from 0 to 3, my over approximation would have been 2 plus 5 plus 10. That would have been around 17. Do you see, from 0 to 1, what's the greatest the function could have been? 2. From 1 to 2, it could have been 5, and from 2 to 3, it could have been 10. My underestimate would have been 1 plus 2 plus 5, right? Now, if I wanted to get better, what I could do is I could go to my table set, and instead of using delta t as 1, I could do 0.5 and go back to my table. And now, from 0 to 0.5, what's the furthest it could have gone? 1.25. Here's the important thing, though. It could have gone 1.25 from 0 to 0.5. So, in this case, hold on. Shoot. I'm running out of room. All right, let's see. That didn't work, did it? Let me try that again. All right. Clip. Okay. So if we're just looking from 0 to 3, here, delta, I'm going to call it delta, what's delta x? 0.5. What's n this time? How many times am I going to add these up?
6.
From 0 to 1, 2, 3, 4, 5, 6. Because I'm not going from 0 to 3, I'm doing all the intervals in between, so n would equal 6. The one we did before was delta x was equal to 1, and n was equal to 3. This one's going to give us a better approximation. All right? So look, we've done a lot. I don't know if it feels like it, but we really have. We looked at graphs, we looked at tables, and we looked at how to count up area. And we learned a lot of different techniques. And your first opportunity to sort of practice is tonight on the homework. Some of the problems are going to feel like, oh, all I need to do is count this, or do it like the table like we did in class. Some of the problems are going to feel like, okay, I'm going to need to read and think about it. And it's okay, because we're going to spend 2 nights with this first section, because it's really important to understand about area and accumulation. All right? So, all things said, not too bad. It could have been worse. Maybe not. Okay.